The Danish scientist Hans Christian Ørsted rediscovered in 1820 the effect of electrical current on magnets. This effect was first discovered by Giandomenico Romagnosi in 1802. The compass needle is deviated by the electrical current in the wire. In 1875, Henry Rowland discovered that a rotating electrically charged disk has a magnetic field. These two experiments seem to prove that the magnetic field is a result of electron translation. Is that true? It was concluded that the electron intrinsic magnetic field would result from the rotation of the electron charge, which thus have a dipole structure. Is that true? The Climont experiment is intended to show it is not in both cases. The magnetic field of a cathode ray is measured before and after a 90 degrees bend obtained by Helmholtz coils, then by an electric field. Is there a magnetic field after the bend? This is the Climont experiment principle. Cathode rays have a magnetic field. It is demonstrated with an electron gun from a Narva PR2 tube made of ordinary glass inserted and glued into a 42 mm diameter borosilicate tube. The tube was placed under vacuum. The degassing of the glue only allows the tube to be used for a few dozen of minutes. A target placed at the other end of the tube allows an electron beam intensity of approximately 0.5 mA to be measured. The magnetic field of the cathode ray is less than 10 × 10⁻⁸ Tesla. The only usable means is the induction coil. The anode of the electron gun was supplied with 350 Vc 50 Hz rectified but not filtered. This results in a 100 Hz pulsation of the intensity of the cathode ray and therefore of its magnetic field. This pulsation of the magnetic field of the cathode ray induces a voltage of millivolts in the sensor made up of 12 coils of approximately 1,400 turns each. Cathode rays do indeed have a magnetic field. However, scientists have known for a long time that electron, proton, or ion beams at the exit of cyclotrons do not have a magnetic field, although these particles move at speeds of several tens of thousands of kilometers per second. They attribute this cancellation of the field to a field resulting from the electric charge of the tube at the exit of the cyclotron. One may wonder how this field is informed of the amplitude of the magnetic field of the beam in order to be able to cancel it. There is, however, a more rational explanation. The magnetic field of the beams and therefore of the electric currents does not come from the movement of the electrons. It comes from the intrinsic magnetic moment of the electrons. Now this intrinsic magnetic field of the electrons was measured by the coils of the cathode ray tube. The coils are therefore crossed by field lines which necessarily have a rotational structure. The intrinsic magnetic fields of electrons are aligned in the direction given by the gun, but as they then rotate in the cyclotron, the beam no longer has a magnetic field. The aim of Climont's experiment is to confirm this phenomenon. The electron gun is now inserted into a tube that is bent at 90 degrees in its middle part. Two targets have been placed in the tube. These targets are connected to milliammeters, intended to check the presence of the cathode ray before and after the bend. The anode of the electron gun is also supplied with 350 volts rectified but not filtered alternating current. This results in a 100 Hz pulse of the intensity of the cathode ray. This pulse induces a voltage in the sensors. The first sensor is the one for measuring the magnetic field of the beam. The second sensor is practically identical to the first with 17,530 turns compared to 17,050 for the first sensor. These sensors were subsequently replaced by a winding of 1000 turns on ferrite toroidal rings. The sensor signals are sent to two AD820 integrated linear amplifiers. The gain is 400. The offsets are not corrected. The amplified signals are sent to an analog-digital converter connected to a USB port of a computer equipped with a digital oscilloscope. When the electron gun heating element was energized, the lanthanum hexaboride cathode evaporated. This resulted in an electric arc between the anode and the gun body after about 20 seconds when the anode was energized. There is unfortunately no such device with a beam intensity of a few tenths milliamperes, allowing for a relatively accessible magnetic field measurement. The guns still manufactured do not exceed the microamp and moreover are powered by several thousand volts and are intended to laboratory use. This is also the case of the electron guns of the old cathode ray televisions. In order to calibrate the measurement device, an electrical wire is crossing both sensors. This wire is also supplied with 9 volts DC rectified with an adjustable resistance so that the current may be set up to from 0 to 1 milliamps. The sensors can detect without difficulties the magnetic field produced by a current of 0.56 milliamps pulsed at 100 Hz corresponding to the current of the cathode ray used. Rowland's experiment is usually presented simplistically by a compass being deflected by a rotating electrically charged disk. The reality is much more complex. There is only a magnetic field near the edge of the disk as seen in this photograph. Rowland used a sort of circular capacitor. A rotating conductive disk, positively charged, was placed between the negative plates of the capacitor. 2 compasses hang from a thread. The lower one is placed on the edge of the rotating disk. The small deviation, resulting from the magnetic field, is detected by a mirror attached to the wire. The rotational magnetic field is the integral of the fields of the loops traveled, from the axis of the disk to the edge of the disk. It is therefore maximum at the edge of the disk. Within the framework of Maxwell's theory, this rotational magnetic field has a component in the plane of the disk, if it is measured above the disk, or in a plane perpendicular to the disk, if it is measured on the edge of the disk. Maxwell's theory ignores the fact that electrons have angular momentum. In reality, when the disk rotates, the angular momentum of the electrons statistically align with the axis of rotation. And so the orientation of their magnetic field changes. It is precisely this orientation that is the cause of the magnetic field of the Rowland's disk. A conductive disk is placed in the magnetic field of a magnet. A brush makes it possible to collect the current at the periphery of the disk. When the magnet rotates, while the conductive disk is stationary, no current is detected in the disk. Faraday thought that the magnet's field, with its flux lines, remained stationary as the magnet rotated. It is true that all field lines are identical. Nothing would therefore modify the behavior of electrons. On the contrary, if the conducting disk rotates, it is traversed by a current. This paradox surprised Faraday. He expected to observe no current, since no current is observed in a circuit when the magnetic field and the surface are invariable. Faraday's law concerns a variable flux of the magnetic field. Relativists have given an explanation based on reference frames. The speed involved in the Lorentz force would be relative to the reference frame in which the measurements are made, therefore in the laboratory. They therefore affirm that there would be a movement of electrons in a magnetic field and therefore a Lorentz force perpendicular to the field lines and to the tangential speed of the disk. The resulting radial current would be collected by the brush. Why would this current not exist when the magnet rotates? Wouldn't the movement be relative? Wouldn't the speed of the magnet belong to the same reference frame? This mathematician's explanation ignores the fact that electric charges have angular momentum. In reality, when the conductor rotates, the angular momentum of the electric charges statistically aligns along the axis of rotation. The intrinsic rotational magnetic field of the electrons behaves like that of a current line. The current lines attract each other, but since the number of electrons is higher at the periphery than at the center, the electrons are attracted to the periphery. The excess electrons are collected by the brush. The movement of the electrons is not the cause of the magnetic field of electric currents. The electron's own magnetic field has a rotational structure and is the sole and unique cause of the magnetic field of electric currents. As a consequence, the magnetic field of the electrons cannot be directly the cause of the magnet fields. It is necessary that the electrons are organized into ring structures in the matter of magnets. Electrons of magnets included in such structures generate a magnetic field similar to that of the magnets. Such a provision might allow envisaging a quantitative explanation of the Barnett effect by precession effect. In the Barnett effect, rotating a magnet changes its magnetic field. The angular momentum of the toroidal structures is in their axis. These structures are precessed. Their axis will tend to align with the axis of rotation. Now the axis of the angular momentum is also the axis of their magnetic field. This results in a change in the magnetic field of the rotating magnet. The Einstein-de-Haas effect was predicted by Ampere as early as 1820. The magnetic field of a solenoid carrying a current causes the orientation of the toroidal magnetic fields of the magnet in the axis of the solenoid. The magnetic field of the solenoid causes an additional alignment of the field of the toroidal structures of the magnet in the axis of this field and therefore also of their angular momentum. This results in a rotation of the magnet by this additional angular momentum. A consequence of the Climont's experiment is that the Maxwell-Ampere equation is false. The magnetic field of an electric current is equal to the geometric sum of the magnetic moments of the electrons in the conductor. The second term of the second member of the Maxwell-Ampere equation makes no sense. Magnetic fields result exclusively from the magnetic fields of the electric charges. The magnetic fields which occur during charging of the capacitors results from the orientation of the electron magnetic field by the electric field. The suppression of the displacement current invented by Maxwell, to solve a mathematical divergence problem has another consequence. The Maxwell-Hertz equation makes no sense. If the waves of space result, in particular, from the electrons' vibrations and if they have an effect on the electrons, there is no evidence they are electromagnetic in nature by themselves. The electromagnetic nature of light is a pure postulate of Maxwell. Light is a wave phenomenon. Since Hertz's electromagnetic equation is undulatory, Maxwell immediately thought that light is therefore electromagnetic in itself. The aim of the positivists, and therefore of Maxwell, was to find mathematical equations for all the phenomena of nature. So the problem seemed to be solved. But there was another serious problem. The Maxwell-Hertz equation is based on the belief that magnetic fields result from the motion of electrons. This equation is therefore not invariant in a Galilean reference frame change. But as we have just seen, this is not the case. Speed plays no part for angular momentum. The problem of relativity does not therefore exist at all. However, some time before relativity could give the illusion of solving a problem that did not exist, the same basic relations, the Lorentz formulas, made it possible to explain the apparent impossibility of measuring the displacement of the Earth around the Sun by the famous Michelson experiment. It was a very convincing coincidence, it must be admitted. Unfortunately for the relativists, by renouncing the absurd equations of Maxwell, everything takes another dimension. By renouncing to postulate that the light would be electromagnetic in itself, it is possible to come back to a medium in space carrying waves such as light, the ether. So Descartes was right. Gravitation and light are carried by the same medium. This is the famous theory of whirlpools. Before going into the detail of this theory, it should be recalled that Descartes' theory explains the Michelson and Sagnac experiments in a perfectly obvious way. Most remarkable is that Descartes had foreseen the deviation of light by the Sun.